Hello and good morning everybody for a new session of computer vision. So today our main topic will actually be generating images, but before that I would like to spend some time to discuss some different network architectures. So this came up actually in the class last year, and it turned out that some people have seen a lot of different convolution networks like the Inception network or the ResNet network, but some of you might not have, and so I would like to discuss a little bit what the trends and the typical possibilities are to design a neural network, and then in the second larger part we will look at generating images. So let's first look a little bit at this topic of different network architectures. So maybe first, all of those networks, how are they compared, or what are they trained on? And one large data set that a lot of networks have been doing and have been trained on is the ImageNet data set, and together with the ImageNet challenge. So this data set consists of a lot of images, like 14 million of them here, different images, and they're organized as nouns. So each image depicts one specific concept, and as sometimes there are different nouns for the same concept, they are organized in what is called a syn set or synonyms. So if there are two words for the same things, they will be put together and then only counted as one class. So for example, there are like over 3,800 different syn sets with animals here. Then the actual challenge on that data set does not use all of the data of these 21,000 syn sets, but it also it uses only 1,000 classes, and usually you looked at the scoring of the top 1 and the top 5 errors. So a top 1 error is you have to guess or predict which class is seen in the image. A top 5 error means you are allowed to give 5 different classes, and the correct image class has to be in those top 5 classes. Here, some example of this hierarchy and of those images. So for example, here we have some herbs, so they are in some vascular plants, and then herb, and then different herbs. And so here you have the different classes then for different herbs. And here with the syn set, you see that, okay, maybe there are like buttercup or butterflower is apparently the same plant, so they're put together, and then those images go together in that class here. So here's some example of these 1,000 classes. So these 1,000 classes for the challenge were not entirely different, but for example, there were different cats used, or different breeds of dogs used. And so then for the classification, you actually had to distinguish between different cats and between different dog races. So not really a very easy challenge. And so this ImageNet challenge was done until about 2017-18, and in the early time, or until about 2012, it was won by a combination of support vector machines and features. And then from 2012 on, it was always won by deep convolutional neural networks. And we will look at some of those networks now to see how they're different in the network architecture, and also how this network architecture has evolved over time. Also, the results have quite improved over time. So this is the top 5 error rate. So at the beginning, early with the support vector machines, and the features you were about at the 25% error rate, and then with the first convolutional networks you were down to about 16%, and the latest results are about I think 3 point something percent error rate, and this is quite comparable to human performance, which is about or slightly below 5%, because really the classes can be quite difficult to distinguish there. So where do these convolutional neural networks come from? You might have seen this before. This is like the first idea of a convolutional neural network all the way back from 1998 from LeCun. He's still active in the field. So he proposed a convolutional network with just 2 convolutional layers and 2 pooling layers, and he used that on the MNIST data set, so to classify handwritten digits, as you know very well from your first homework there. So then it took quite a while to get off with the convolutional neural networks, that they could be used in more demanding image tasks. Why? Because just 2 convolutional layers are really not enough to recognize more complicated images, and for larger networks there was just not the computational power available to run and train them. So then the first network that won this ImageNet challenge was the AlexNet architecture, and they used 5 convolutional layers, not so many, also max pool layers. They introduced the ReLU activation function, and altogether it has about 60 million parameters in the network. At the end of the convolutional layers, as usual, you have connected layers. They used 3 fully connected layers to do the classification then. So here a bit in more detail how it looked like. So if you will then compare it to some later architectures, there is some things that might be done a bit differently now. One of them is the filter size. So he started with some very large filters, 11 by 11 filters with stride 4. So this will quite reduce the image, and it also requires quite some parameters to learn the filters here. Then they continue with some max pooling. So they used 3 by 3 filters. Now 2 by 2 are used a bit more, and then some more convolutional 5 by 5, so smaller filter, and then 3 stages of 3 by 3 convolutional layers. And at the end, you then have the fully connected layers, and you have to go to 1000 neurons in the last layer, as you have 1000 classes, and then there you will go to the softmax, and you will get the probability of each class. So for training at that time, that was not so easy. So he did have latest GPUs, which at that time was a GTX 580 with only 3 GB of memory. So you had to spread the network across 2 GPUs with half the neurons on each GPUs, and then bring them together for the optimization. So quite a bit of engineering to actually get it running on the hardware. So it was already kind of too large for the hardware at the time, but they still managed. So this is again the results from the ImageNet, sorry, this time from right to the left. And what I wanted to show here is actually the layers that are involved in the challenge. So here this AlexNet network had 8 layers. Also the next year there was a quite similar network that they did also with 8 layers, and then it increased to 19 layers, 22 layers. We will look at those architectures until finally, like in 15, they used 152 layers for the network that performed best, and with that they were able to drop the error rate to 3.57 here. So it seems the trend is to go deeper with the network, and the first network that tried to do that was Google LUNET. So the original name was taken from the LUNET from LeCun, and then just added Google here. But because in their paper they used the phrase, okay, we need to go deeper, and we need to go deeper is from a movie, Inception. So the network is generally known as the Inception architecture because of that. So they used some quite new concepts. One of their ideas was not to use a single convolution at each state, but to have multiple convolutions and then just put the results together. So you don't add the results, so you concatenate the results. So you would have here a layer, you get one pass with 1x1 convolution. This will give you a vector of response. Then you have the 3x3 convolutional, which you add to them, and 5x5 convolution, and you add, and you also do a 3x3 max pooling, and you add them, and this will be the result here. Okay, when they did that, it turned out that then the network will have quite a lot of parameters, because if you have like 256 channels here and you do 5x5 convolution to another 256 channels, then this will be a lot of parameters. So they came up with a concept that has then been known as bottleneck layers. And the aim of that is to reduce the parameters that you need for that convolution. So for all those convolutions that need a lot of parameters, they did not apply them directly, but first added a 1x1 convolution that will go down to to a fewer number of channels here. And then you have a fewer number of channels, and then you can do your filter, and your filter then will have less parameters, but it's still better than to have less channels altogether. So again, those bottleneck steps are 1x1 filters that will go from a higher number of channels to a lower number of channels. So for example, you have the image at that stage during processing would be 56 by 56 by 64 channels. Then you have a 1x1 convolution with 32 filters, and as a result you will then have the image of the same size but with another number of channels here. And if you do that using convolutional, then you expect that it will learn how to process those 64 channels and still remain as much information as possible. So maybe combining some channels or maybe eliminating some channels because they're not needed with those convolution. So it preserves the spatial dimension, but it reduces the depth, so the number of channels that you will have at the end there. Okay, so altogether then they came up with architecture like that. So they have those inception blocks here and pull them all together like 22 layers with the inception blocks. And since some of them are in parallel, altogether they have about 100 building blocks here for their network. And so this is the inception network. More generally, this is called the inception version 3 network that they present here. So at that time, in order to train them, there was a problem training deep neural networks, and we will later see two solutions, or we already have seen two solutions for training deep networks. One is the ResNet architecture, we will see later, that helps with training deep neural networks. And the other thing that came later was the batch normalization, which was not present at that time, and that also happens to help with the training of neural networks. Since they didn't use that at that time, they did the training in stages. So like they trained all of this here first, you see, with some fully connected layers here, and then they have a reduced network that is already able to do some classification, but not good enough yet. Then they use those weights as an input to train a deeper neural network with 3 more layers here, and then again the classification stage here, again train it, and when this is trained, then they did the same again. So they trained it 3 times until they finally trained the whole network then. Okay, so after the inception network, the next network that came along was from Simonian and Zisserman from University of Oxford, called the VGGNet, and they tried different depths of networks and seen which networks performed best. So one change is that they got rid of the filters of different sizes and just use 3x3 convolutional layers only, and with some pooling. And here is a depiction of one of their networks. What they also did is they just increased the number of channels after some layers. So here after every second or third layers, and they just doubled the number of channels until at the end they have 4096 channels as input for the convolution, for the classification stage. So that would be like the features that you get, and then you do the classification to get to the 1000 classes. So more in detail, and a comparison of 2 of their networks with the AlexNet, so the VGG 16 and 19 with 16 or 19 layers. You see that AlexNet had those larger convolutions here, and they just used only 3x3 convolutions. Why? The idea is that if you have a stack of 3x3 filters, you will have the same receptive field. So for the output, you will look at the same neighborhood of the image as a 7x7 filter. But you actually have less parameters. With a 7x7 filter, you have 49 weights, while one 3x3 filter only has 9 weights. And so if you have 3 of them, you have 27 weights, which is less than one of the 7x7 filters. But since you have 3 layers, you have introduced more nonlinearity, and this often helps because the shape of the function that the network actually has to find for the classification is not linear. So this is the idea: deeper networks with less filters instead of shallower networks with more channels. So here some details of the VGGNet 16. So this would be the input size. So in the image channel challenge, the images were quite small. So 228 by 228, and at the end you will need the 1000 classes as one by one to give you the probability of each class. And you see that the convolutional networks, the convolutional layers, depending if they use valid padding or same padding, they reduce the number. So they used same padding here, so the size stays the same, but then obviously if you do a pooling layer, then the size of the image goes down. So with every pooling layer you have half of the image size, until at the end of the feature stage you are at the 7x7 image. So it might be interesting to look first off where is most of the memory spent, and where is most of the parameters spent in this network. And if you look at the memory, so this is the memory that the computation needs to hold its results and its gradient and its parameters. That will be usually early in the network when the image is quite large. So for example, use 3.2 megabyte here of memory here. And of course then distributed over the GPUs. This could be one of the bottleneck then to train it on the GPU. While most of the parameters are when you go to the first fully connected layer, because you still have most features when you enter the fully connected layers. So on your first fully connected layer, you will have most of the parameters of the network. While the parameters of the convolutional layers are still large number, but nothing compared to the parameters here. Okay, so next step was to try actually to make the networks deeper and deeper. But if you just add more 3x3 layers, you would think it would get better, but the problem was it did not. So for example, here just sketched the performance of a 20-layer network and a 56-layer network, and the 56-layer network performed actually worse than the 20-layer networks. And it's not from overfitting, it's worse on the training and even worse on the test data set. So there must be something else. So what was the problem to not be able to make the network deeper? So the idea was, if I already have enough layers for the network to perform the task, if I add more layers, it shouldn't get worse, it should at least remain the same, or maybe even get better if those layers can actually be put to some use. But it should certainly not decrease the performance. But this is actually what happened. And why did this happen? Because those additional layers, if they should not do something, then they have to learn to leave the image or the features at that point to where they were before. So they would actually need to learn identity transformation. But layers are usually initialized close to 0 and some random noise in the vicinity, and so it's not so easy for them to actually learn the identity transformation, and they did not. And the solution that He et al. Came up with was to have a shortcut here. I come just back to the question just a moment. Is a shortcut here so that you have your input data here, then you have 2 layers with some convolution, and then you have the output here, and at this position you add the values that you had before, and this time you really add them, not concatenate, to the results of the layers here. And the effect is, if those layers do nothing, so if they output 0, then you would still have the same as you had before. So question was identity transformation is that you actually leave the values that you have exactly the same, that you will have the output again as before. So it's like you add a layer, but it does not change the result, and then it will not get worse. And now with this shortcut here, so this is called the residual connection. If they do nothing here, then you will really end up with the identity transformation. And since the layer weights are initialized close to 0, it's much easier for them to learn to put the input to 0 than to put the input to the identity. Okay, so the idea is you have those connections here. You can just add layers, and they should not disturb at least the results that you had before. And so they tried this first with a 34-layer network. So they organized a bit similar to the VGG, but also took something from the AlexNet. So they started with a 7x7 convolution at the beginning, and then they just had blocks of 3x3 convolutional filters with like the VGG increasing channels 64, 128, 256 to 512 then. And this would be just a plain network, and then this would be the network with the residual connections. So every two layers you have those residual connection, and they don't need any parameters. You just have to add the input from before. So this is quite easily actually to do. Oh, okay, here another application of the network, and actually there is some variant of the ResNet with up to 152 layers, which just continue like that, and they were able to train that network. Then for really much deeper networks, they also came up with the combination of those bottleneck 1x1 convolutional transfers together with the residual connections. So so you want to go from a 256 to 256 channels, but as we have seen, 3x3 convolutional with that number of channels requires quite a lot of parameters. So they used two 1x1 convolution. First one to get to 64 channels. Then you had a 3x3 convolutional to get to again 64 channels, and then you kind of upscale the channels again to 256 channels, so that you have the same amount, and then can add the input here for the residual connection. Okay, yes, you could use 3 or more layers. The question was 2 layers is kind of arbitrary. I'm sure they tried out some different architectures. I think 2 is also already a compromise. You could use just 1, but if you skip too many of them, then maybe it's not as efficient. Yeah. Yes, they help. So they help with the gradient propagation. So with vanishing gradient problem, that could have different sources. One could be a really saturated loss function, or just layers that do not have any activation, and then you would also have a vanishing gradient. And in that case, that the layers do not have any activations or values, then it actually helps. So because you can see it's propagated here during the calculation, and of course when you go back this step, it also propagates the gradient from here to here back. And so the gradient will flow through the network even if those layers do not do anything. While before, if those layers do not do anything, then the gradient might vanish, and then you cannot do anything on the earlier layers there. So with this ResNet architecture and this combination of bottleneck layers and ResNet connection, they were able to train very deep networks of 152 layers, and now the deeper networks were better than the more shallow networks. So there was also some other challenges. I mean, you might have heard of that, the COCO data set. I think we looked at it quickly, which also have a detection stage, and they also applied it to there. So in 2015, the ResNet just won all first places in all of the challenges at that. So still today, this is still used, this ResNet architecture, and then they also try to incorporate it to the inception architecture. So there is a combination of inception architectures and ResNet ideas. So from the inception architecture, you have the idea to use different convolutions at the same stage and then concatenate them together. And for the ResNet, you have those direct connections here. So for the ResNet V, they used a bit different building blocks. So for example, instead of the 5x5 filters they had before. They also used combinations of two 3x3 filters instead of a 5x5 filter, which also has the same input area receptive field. Or they tried separable filters. So separable filters is filters that are in one dimensions. So for example, a Gauss filter in 2D can be calculated as a Gauss filter in X direction, and then the result a Gauss filter in Y direction. And they did something similar here, so a 1/7 convolution in one direction and then a 7/1 convolution in the other direction. Concatenate is just as a double, so it's really just a vector. So in one of those passes you might have as a result 64 channels. So you have a vector with 64 values, and then from another pass you have another 64 values, and you concatenate those vectors together to form a vector of 128 channels at the end. So it's concatenation of the vectors and the result at that position in the image. Okay, if you look at some comparison of different architectures, then over time, so we see some different results, so they can be better or less good. In this here, it's the top 1 accuracy in the ImageNet, and they can use a more or less operation. And the size of the bubble here is then also how much memory they use internally. So that also depends a bit on the filter here. So I think it's quite a nice overview. So the AlexNet in the beginning used actually quite some memory, not so many operations then that have to be calculated, but okay, the size here is the size of the parameters that it needs, and the GOPS is how much actually the calculation is when you go through the network here. So there were some networks with like early Inception, GoogleNet and Inception version 3, which were quite a lot of better than the early networks here, with only a small increase in the parameter and a small increase in the computational power. And so then the ResNet with even a very large deep network like ResNet 101 here, you get a very good result, just moderately more parameters. Why? Because with the usage of those 3x3 parameters in 3x3 filters instead of the 7x7 filters, you actually save on some parameters. And so at the moment, the kind of best result at not so much more parameters and not much more cost is the Inception version 4 network, which is this combination of ResNet and Inception. Okay, so I think that's kind of the main result. So the state here today still does those ResNet-like architecture with deep networks and small filters seem to be best. So there have been some more approaches. One is that they reordered actually the mappings in these residual connections. So this is from the same group that made the ResNet, and they could make it a bit more efficient than with the order when they do the batch normalization, the activation, and then the actual filter operation. And one more approach was that somebody tried, okay, actually ResNet is fine, but it's not all about the depth of the network. It's also valuable to make the network actually wider with just more filters at one stage and make some residual connections there. And so they introduced some wide ResNet, which was then better in 50 layers than the 152 layers of the original network motivation for that is that if you increase the weights instead of the depths, it's a bit more computational efficient to run on the GPU. Okay, so that would be all for the first part here, with some just overview of how deeper neural networks are built now. So I would suggest we make a short break of 10 minutes, and then we will look at a new topic of generating images using first some model techniques and then some convolutional neural networks for that. Okay, or any questions? Or maybe otherwise after the break. So short break, 10 minutes, and see you in 10 minutes. Upload solution last week, I will look into that if I haven't opened that yet. Sure. Okay, welcome back. So last week we actually we did some object detection, and a week before was semantic segmentation. So we were all in the topic of recognizing things. And so for this lecture, and we will also have a short lecture next week. We will look at something different, and we will look at generating images. Yep. So why do we want to do that? Well, it's actually quite a fun topic. So idea is, or one of the motivational ideas here is that you can try to generate realistic samples. So here, these are all images of people that do not exist. So they were just generated by learning how to generate images of faces here. Or also here, those bedrooms, there were no actual pictures, so that was also a neural network that learned to generate images of bedrooms. Some other, maybe a bit more practical examples that we will a bit more actually look then in the next lecture is image-to-image translation. So, for example, if you have those labeled image, you can actually train a network to reproduce a photograph or a scene from that. Or, for example, if you have an aerial image, you can do something like destruct a map out of it, or labels to how a facade look like, you see. Or you could just have some conversion. So for example, you could train networks to add color to images. So when you have black and white images and you train them on a lot of color images, they can actually colorize the images. So for example, you could use that if you want to colorize some old black and white movies. Or you could transform images from how they looked at daytime, and you learned the network to produce images for nighttime, and then you can transfer any images from daytime to nighttime. Or edges or just sketches, and it fills out a real object for it. Or for example, image completion. So here there was something in the image that you had to cut out. It could not be shown, but you would like to have the rest of the image filled in so that it's not noticeable, and you can learn to generate the image in just that part. Or you have that image which has text all over it. You want to get rid of those texts, so you can do that in Photoshop, but it will be very time consuming to do that and then really paint and fill over it. Or you could use a generating image approach to actually automatically produce that image with the text removed from this image. And you see it looks quite good here also in the details. Okay, so we will look at some of those transformation and also of style transfer and deep dreaming in the next lecture. And in this lecture, we will just look at generating images from, well, other images that you have been trained on. So the idea is you have given a training sample of only images. You don't need labels or anything. And what you would like to do is to generate new images that come from the same distribution. So if your distribution was like interior of apartments or maybe bedrooms with beds here, then a sample from the same distribution would be also an image of a bedroom that you want to generate. I don't know how they came up with that idea, but maybe they needed new ideas for decoration, and so then could be some inspiration of how to do that when you first do it with generation techniques. So how can we do that? So there's actually different possibilities. So what do we actually want to do? We have some distribution pay data, and we would like to learn a distribution pay model which we don't actually have, we only have data for it, so that we can then draw samples from P model to get the images. And two possibilities is, well, really just solve and try to find this distribution of P model that would be an explicit density estimation, because you would like to approximate this distribution here. Or implicitly at the end, we don't actually need the model distribution. We only want to be able to sample from the distribution. So we could also just learn a model that can sample from that model distribution without having the model explicitly. Okay, so general, we can say these generative models have these two possibilities, implicit or explicit. And for explicit, there are different possibilities. Using convolutions directly to get pixel distributions, variational autoencoders. There's also called Markov chain model, and for the implicit density model, there are GANs and Markov chains models. We will look not at all of them, but just at 3 of those approaches today, so that you have seen a bit what it is about. And these are also, I would say, the most popular approaches in the field. So one is the pixel RNN, CNN, variational autoencoders, and then the generative adversarial networks called GANs. Okay, let's start with the first one. So this is an explicit density model. So you would like to learn the distribution of your image, and the distribution of your image will just be some probability value that any pixel at some position has a specific color. And using a model likelihood means that you would like to have the probability that the pixel has some certain color dependent on the other pixels that you already have in the image that you maybe have calculated before. And during training, you would try to maximize the likelihood of the data so that it fits the model that you learn here. So one idea is you can have a model using a recurrent neural network, so-called, which you can build with different techniques. So we didn't discuss it here. One building block is this long short-term memory approach to recurrent neural networks. And then it keeps a state and it gets some additional input at each stage. So what you do is you will predict one pixel value, and then when you go to the next pixel value, you get the input from the neighbors that you have already calculated, and will predict the pixel value for that, and so on and so on. And you go through all of the image pixels like that with your model. And at each time step, you have the input of those neighbors that you have already calculated. And this works because you will then have those input here, and you have the probability of the color of this pixel is then influenced by the colors you have assigned already at this level here. In a later approach, they then pushed out the recurrent neural network and instead used a pixel CNN convolutional neural networks for the same approach, but still with the same idea. You generate the images from the corner, and you have a convolutional neural network over a region, and in this region you will have those pixels that you have calculated already, and you will ignore the pixels where you have no value yet. Okay, here are some examples of what you can produce at that level. So there are small images, but I would say in most of the images they're not perfect, but you can recognize of what is meant by the image. So for example, the dogs here, they all look like dogs. So this one here might be quite nice, and with some others it's not quite clear where maybe the dog ends and some other object here appears, but if you just show it to somebody quickly, he will say, yeah, that's probably a dog. Yeah, same tigers, some are quite good, some are a bit confused here. Okay, there was a question, another lecture next week. Yes, so because of the break that we have for 1 week, we had gotten the option to add another week, and would make use of that option so that I could split the lecture here, as I have last year in 2 parts. Otherwise, it will be a bit too much. But it will just be another input for a bit shorter. I think maybe 1 hour or so then next week. Yeah. Okay, so this first approach using pixel RNN or pixel CNN, they can actually model the likelihood of the image. So it's good samples. It's quite high resolution, the images, but maybe in the overall structure of the images, they're not always that clear. And it is quite time consuming to calculate there. So next approach to generate image are variational autoencoders. So how does that work? So before we have a distribution that depends on the other pixels already set. With variational autoencoders, we try to model it from what is called a latent variable space. So we have another distribution of so-called latent variables, here called set. And then we try to learn how to transform those that space of latent variables using this integral and this probability function to get the value, the probability of x. So a pixel having a specific color at a specific position. Okay, so you will be given the latent variable space. We have to learn how to find that, and then the variation autoencoder can generate from those latent variable space the image using that transform here. Problem is a bit that integral cannot really be computed directly, so there is a lot of tricks a bit involved to make it work here. But before we look at variational autoencoders, maybe we should look at autoencoders first in general. So autoencoders also come up in other topics of supervised and unsupervised learning, and it would be how to learn a good feature representation for the data, and with a feature representation, something that is lower dimensional as the original data, but captures the important information of the data here. So we can look at that like that. So we have an image. An image will be from different classes, but it doesn't really matter. But you will have a lot of training images, and the encoder step will transfer that image x in some variable space z. So for these encoders, earlier we used some usually some linear model with some nonlinearity. Now you can just use a convolutional neural network to learn the transformation for your image to your encoder space. And the important thing is that your space z should be smaller than x. So you want a dimensionally reduction here. So the space of x is, of course, you have the image, you have a pixel at each point, so you have a lot of variables, input variables here, and you would like to have a condensed representation of that image using some smaller set of variables, which we will call z. But z is supposed to capture all of the images here. So how can we train a neural network that it finds some meaningful representation of our image with less variables? Well, we train another part, a so-called decoder, that learns how to reproduce the image from Z. So the decoder will learn the reconstructed image. Okay. Earlier it also used to be another linear transformation with sigmoid. Now we've seen how we can use convolutional neural networks to make images also larger, so we can use upscaling convolutional neural network. Okay, so how do we train that? Well, actually, we can do that quite easily. So we want to have our reconstructed image to be as similar as possible to our original image. So we can just have a loss function, which is the difference between our reconstructed image and our original image. And this we can train. We do not need any labels of the image. We just have to make sure that it has to go to a representation of Z which has less parameters than the image. Okay, so we could learn that. And how can you use such autoencoders? One possibility is that if this really works, then you have all the essential information of the image in the variable Z. So if you want to classify the image, instead of using the image X, you can use the variables Z. So you could throw away the decoder and then just have use it for classification and use that representation as features, and then train a classifier to actually get the classes from your encoded space here. That could be another neural network, that could be something else like a support vector machine. So, So if you use those encoder and decoder step of the autoencoder, the decoder can reconstruct the data from some internal latent variable space Z. And the autoencoder can capture what is meaningful about the image in Z. So how can we use that to generate the images? Well, the idea would be we can just now, if we have some Z, then we can just maybe use another Z and try to reconstruct an image from that. So this is the idea behind the variational autoencoders. So once we have learned how the latent variable space looks like, we sample from the space of all Z, and then from that space we can reconstruct the image using the decoder. Okay, now there is a little bit of problem with that, and that is how that latent space actually looks like in general. So if you just use a standard autoencoder, then the representation of the latent variables might not be easily interpolated, and it might not make sense in all the parts of this latent space. So here, for example, is using an autoencoder of the MNIST data, and we have the so the encoder is two-dimensional, so that's quite small, this product. And here is the distribution of the different classes that you have in that latent space. So every one of those points is the auto-encoded or the encoded representation of some input image of, for example, the number 7 here. And so now you could go and maybe if you take some point here where you have a lot of 7s, and then you learn how to decode those variables, you will probably get something that looks like a 7. And here you will get something that looks like a 1. But what happens, because you don't know how your space looks like, what happens if you take a value here? This is not some meaningful value that appeared in the MNIST database, so you will not get something that resembles any of those images that you're trained on. So the problem is that your latent space is, well, you don't know how it looks like. It might have some gaps, and you can not just interpolate and get some meaningful result here. So the idea behind the variational autoencoders is that you want it so that your latent space, the distribution of your latent space, is simple and, for example, a Gaussian distribution. And if this is a Gaussian distribution, then it's easy to sample from it. The decoder part that will calculate your image from your latent variable is then very complex, but you can model that with a neural network. So you have to force the autoencoders to build a latent space that can be approximated by a Gaussian. And you can try to compute that it is like that, and that you can calculate it at the end with the integral. Problem is some parts work well, so we have said that this transformation from z to x, so this density function, actually this can be modeled by a decoder neural network. Okay, we have seen that the distribution of the variable z should be a Gaussian, so this can also be modeled, but the problem to calculate this integral then is not really possible for every value of z. So this is just intractable. And then from that you can also, if you want to have the posterior probability densities, so you could use Bayes for that, as unfortunately also intractable. And what you then do is you define a network that approximates this density distribution, and then you could use that to calculate the integral. So then there is a lot of math involved. So the integral, here it would be symbolic, or also, I mean, numerically, you cannot numerically solve it beforehand, because you would have to go over all the space. So that's just too much computation power, and symbolically, yeah, you cannot solve it. Yeah. And so what they came up with is with some manipulation, you get something which is still intractable, but it's possible to calculate some lower bound, and this lower bound can then be used to generate the actual decoder function and to calculate the result here. Okay, so what you end up with the variational autoencoders, so the math details are quite complicated, so but I also think it's not necessary to go into deep in there. But the essential property is that with your encoder network from your image, you learn a representation, and the representation is a Gaussian representation. So that means every variable has some mean value, and it has the sigma, which in higher dimensional space would be a matrix instead of a single sigma that you have in a Gaussian, and this characterizes your latent space. Then you have your latent space, and now you can sample from that latent space. You take a mean value, and you know the derivation, so what you can sample from. So you sample from a Gaussian distribution with mean values and the sigma that you have, or a covariance matrix, and then feed that into the decoder network, and this will give you the image. So the difference between the autoencoders and the variational autoencoders is that the distribution here is Gaussian, and you know the Gaussian distribution so that you can sample from it. So once you have learned all that, you can just sample from Z and then reconstruct the image. So here's just some examples. So what have we done here? We have done trained a variational autoencoder on the MNIST database, put it into a two-dimensional space, and then just picked one value there from that space, and then generate the image of that space. So you see, you get some 1, 2, 3, 4, somewhere around here. So they are all represented somewhere in this lower dimensional space. And for example, you can play around with the space of your latent variable. So you give this as input, how much compression you want to have. So for example, in MNIST, if you do 2D latent space, you get that result of generated images. If you do a larger latent space, you will get some clear results, because I think here there are some cases where it's not sure if it's maybe a 6 or an 8. And here it might be a bit clearer. And if you go to a more dimensional space, you get clearer and clearer. But of course, if you go above a 10D or a 20D latent space, does not really make much sense in that case, because you only have 10 classes to begin with. Okay, but it's quite fun. You can do some nice things work around. So maybe in your latent space, it could be that then some degrees in your latent space manipulate one aspect of your image. So if you change one variable, it could be the degree of smile, and another variable could be the head pose, and they are independent of each other. So by sampling from those two variables, you get some smiley faces in this or this direction, or non-smiley in those directions here. And you can use that to actually generate data. So these are two examples where the variational autoencoder has been trained on the CIFAR data set or on the Faces in the Wild data set. So Faces in the Wild is just a database of faces, and faces look quite nice, but here the what's around the faces is not so clear here. Yes, it would be a multivariate distribution as in the higher dimensional space there. Okay, so together with variational autoencoder, so this is a approach for generative models, and it allows the interference then of that probability distribution. With the mass, it can calculate only a maximum lower bound. So what turns out that the samples are a bit blurrier and a lower quality maybe as the next approach that we said. But there is also in some other areas like audio processing or so where variational autoencoders are used. Okay, the third and last idea for today for generating images are so-called generative adversarial networks, or GANs. So concept was first introduced by Goodfellow and Bengio, who also wrote the popular book on deep learning. So what is the idea here? So the idea here is that we play some two-person game. So we have two agents here. So we have the counterfeiter, and what does the counterfeiter do? He tries to generate dollar bills or fake dollar bills. And what does the police do? The police tries to find out which bills are fake and which bills are real. Okay, so both of them have some objective So the objective of the counterfeiter is to make the dollar bills as good as possible, so that it's not easy to distinguish them from real bills. The police, on the other side, their objective is to learn better to distinguish between the two sorts of bills. And so this is kind of the idea between these generative adversarial networks, adversarial because they have adversarial tasks here that they would like to do. So we actually now do the same with networks, and so because we have those two agents, we also need two networks. So the generator network tries to generate real looking images so that they can fool the discriminator. The discriminator, also a network, gets as input an image, and it has to say it's a real image or it's a generated image. And so it tries to learn to distinguish between the real and the generated images. Okay, so in order that the generator network generates something different each time, we have to feed it somehow different values. So what you usually do is to feed it just some random noise. So this is kind of like the Latin space before, except that we have not learned the Latin space, but we have to give some dimension of the random noise that we feed into the generator network. The generator network then will generate images, fake images, and we know they're fake, so they have the label fake. And the discriminator network has to find out if they're real, if it's real or fake. And we give the discriminator network for training, we give it real images with the label, this is a real image. We give it fake images with the label, this is a fake image. And it has to be able to learn to discriminate between those two classes of images. And then when it gets a new image, once it's trained, it can predict if the image is real or fake. So in order to train that approach, we have to train both networks jointly. So this is kind of a minimal or maximal function then for the expectation. So we have to train that it produces as good images as possible, and that the discriminator, so for the discriminator, it's like a binary or two-class distinguishing approach, which can be formulated like that to discriminate for the real images and to discriminate for the fake images. So for one of them, it should be as small as possible, and for the other, as large as possible. So the discriminator then will put the likelihood of a real image as a probability value between 0 and 1. So the discriminator wants to maximize its objective so that its function is as high as possible if it gets a real images, and as low as possible when it's a fake images. And the generator wants to maximize its generated image out of Z so that its generated out of image is as close to 1 as possible, so that the discriminator actually thinks it is a real image, while G for Z is the generated image from that variable distribution or random variables Z. Okay. So training GANs is not so easy. So there is some things involved. One is that this term saturates early, and so you can write it a bit differently. So it's better to maximize this function here. So this helps a little bit. And one other problem then, if you do that, so Okay, first let's look at how to train that. So you just sample some noise samples from some prior function that you have given with some specific dimension from your noise samples, and then you will generate the image and calculate the term, and then you train it as usual by calculating the stochastic gradient and then maximize in that direction. So usually you do some steps for updating the discriminator and then some steps for updating the generator. And there are different philosophies here. How much steps should you do for that? How much steps you should do for that? Is it better to have a number of steps for one side and a number of steps of one side, or just one? So this has been experimented a bit. I think it came out that it's better to really alternate between those two. One of the problems a little bit is since you train something that is a minimum and a maximum, in that term you essentially have some surface that is like a saddle point. So it's a maximum in one direction and it's a minimum in the other direction, and this is numerically not so stable, and so this is what makes training guns quite difficult. There is now not so new, but like I think 1.5 years ago, some new approach, so-called Wasserstein gun, that uses some special numerics to train guns that came up, and with that approach it becomes much more stable. So this was from OpenAI. Okay, so once you have done that, then of course you're not really interested in the discriminator anymore, but just in the generator. And now that you have the generator, you can just feed it random noise, and it will give you images. And your random noise that you feel is in some dimension, so you could use 2-dimensional or 10-dimensional space, and you can actually go back and find out what the dimensions of those spaces mean. So for example, if you use the space and you generate always smiling women, and you use that the vectors, the latent vectors from that space, and you use the vector from when you only generate women that are not smiling, and then you add the space of men, you get smiling men. Okay, you can do some kind of vector mass with it. So smiling woman minus neutral woman means it's just a smile left. So you will have discovered the dimensionality of where is your smile in your latent space. If you add a man, you actually get a smiling man. Quite fun. Or you can do it with glasses. So man with glasses minus man without glasses plus woman without glasses gives you woman with glasses. Okay. So this is the idea behind GANs. We had internally one project with GANs. So we were asked from some barista that they have to come up with new images, so ideas, images to put on their coffee. So usually they're quite exquisite here, what they can generate with milk and coffee on your coffee cup. I'm never able to get anything. Well, for me, it's just a big white blob when I try that. So, but they can make real images, and they wanted to come up with some new images, and they asked us, actually it was Daniel Peffley from our lab, to use a GAN to generate new images from those examples. So they gave us a lot of images from coffee cups, and the images made on them with milk and coffee. They use that as a training set to train a GAN and then to generate some images. So result is well, I would say medium convincing. You can we see that it generates something that looks a bit like a cup, and it has the correct color here of patterns of white and brown coffee, but it's not so clear yet what the image then actually looks like. But still, I think it was quite a fun project here. So some of them are, I think, quite good that what can be generated here. Okay, here is some more actually resources if you want to read a bit more about the variational autoencoders, or also the GAN example that used those vector mass here. The idea was for today also another demo or exercise that you could try that out for yourself. I have, unfortunately, when I tried it out again, I kind of shut down my Conda environment, so I didn't get it running. You find the information, the Jupyter notebook on Moodle, and it just puts in the different commands to make the model available from this site on GitHub of progressive growing GANs. So maybe you have more luck with trying out. I will try to get it running again until next time. The problem is the model is about I think 2 years old, so it uses an older version of TensorFlow. So if you have a Conda environment or a Docker image, that would be easiest to install in there. So I think TensorFlow 1.15 or so should work there. So you will find the Python notebook then here. Let me see. Okay. So here you would find the demo to try out, and you can see the instructions there. It's from that website, and here you could also then, there was another link to download the weights, as last time people had some problems with that. Okay, otherwise that would be all for today in generating images. So as I said, we would like to make use, sorry for using this additional space that we have for one more lecture. So next week we would have another lecture and look at more of generating images. So we will look at those so-called deep dream images from Google, and a technique called style transfer, so that you could apply like the style of one painting to another image. So I think this is quite fun. It will be just a bit of theory. They will also hopefully have then the final date of the when our test will be, and will be available then for more questions or so regarding the test. So otherwise, that would be all from my side for today. Will still be available on Discord if you have any more questions. Otherwise, have a nice week, nice long weekend at Pfingsten, and see you then for the last time next week. Bye bye.